your what we say official midterm grade is on my LaRoche. So, I mean, what's on Canvas is on Canvas, but if you want to know what your grade would have been had you had an official grade after the midterm, there you go. I wouldn't really read anything into it, to be completely honest with you. If it's a good grade, that's good. If it's not a good grade, that doesn't mean anything other than you just need to work harder. If you think it's incorrect or you want to talk about it, feel free to do that. I'd be happy to meet with you. I'd be happy to do it on Zoom, whatever your heart desire. But there's plenty of chances to improve your grade if you need to. And even if you have a good grade now, there's plenty of ways for you to make it bad. So please try not to do that. All right, so on the homework, let's talk about it. Problem 2. So the question is, we want to know, whoops, I hit the wrong button. We would like to know what intervals we can define f of x by x squared, and it can still be a bijection. So let f, let's just say it's from A to B right now. Let's be a little more specific, because this is really what the problem's suggesting. So let f be a function from real numbers into real numbers. And the rule is that it's the squaring function. You plug in a number, it spits out its square. So what we'd like to know is, here's what the question is asking. What is the largest interval? And I'll put largest in quotations, because this is, what does that mean? Well, I'm asking you in the colloquial sense, how big can we make the domain so that the function is a bijection? Right? What is the largest interval so that f from, let's say, this interval a comma b into R is a bijection? So there's a lot of ways you can attack this. What you need to know is what a bijection means. A bijection means one-to-one and onto. Now, I don't know what's the safest way to go here, but we have talked about this function before. In fact, we pointed out that it's not one-to-one if we don't restrict the domain. We had that on a previous sort of example we did in class. So here's the way I would tell you to think about it. Here's some scratch work. First, I'm going to ask, is f one-to-one? Or more particularly, when is f one-to-one? So let's remind ourselves what that means. There's a couple ways you can interpret this.
Well, let's assume f of A equals f of B. What does that mean? That is A squared equals B squared. How can we guarantee A is equal to B? That's the question we need to know. If we want to show that this function is one-to-one, one way to think about it is if we have the same output, that implies we have the same input. Now, if I just let A and B be any real numbers, I can't guarantee this because -2 squared is the same thing as 2 squared. -5 squared is the same thing as 5 squared. So I can't guarantee A is equal to B unless I restrict what values A and B can be. Do we understand this? So let's write this in a different color because the observation is if we assume A and B are both non-negative. If they are both non-negative, it's impossible for them to be the same number. Now, here's where you're going to get confused. You're going to get confused because I'm using A and B in two different contexts, and I apologize for that right now. This letter A right here is a generic number. This B is a generic number. It has nothing to do with me writing A comma B up here. So I should have used different letters. I always forget that you guys is sort of amateurs. Let me do that. Let's switch this. It's worth it so you don't get them confused. So let's just use different letters. Let's use, how about we use N and M? So how can we guarantee that N and M are the same number? Well, the only way we can guarantee it is if they are both non-negative. Because if I allow them to be negative, as I said before, I get that -2 quantity squared is the same as 2 squared. So if we go to the next page, we can write this out a little differently. So this means f from 0 to infinity in R is 1-to-1. And let me be even more specific so you don't forget what the function is. Or if you want to get fancy, you can say injective. Now, are there other ways to reason this fact? Absolutely, there are other ways to reason this fact. Another thing to keep in mind, a function is really three things. It is a codomain in a domain, and it is a rule. So that is why I'm writing it. It seems weird, but I'm saying this means F, and I'm being very specific. What is the domain? What is the codomain? What is the rule? So one of the things you have to think about, put this in perspective, most of you are only familiar with functions that take a number and spit a number out, or take a couple numbers and spit numbers out. And that's why most of the examples we're doing right now are those types of functions. But you can imagine that a computer is asked to do tasks all the time. Maybe I have to tell something like I have to tell my computer to go look at a list of web pages and pick something out on there. And there might be a certain rule that assigns each web page with something. That is a function. And so it's not just a rule, like some algebraic rule. A function in general is a rule, which is a very abstract thing that associates two different sets. So that's why I'm writing it this way. All right, so we know that as long as our domain is either from 0 to infinity, that interval, we get 1 to 1. So the question is, what about onto? Is this onto as well? Well, what does it mean to be onto? Well, let's ask ourselves. Take any y in R. Is there x in 0, infinity such that f of x equals y? Well, what does that mean? F of x equals y means x squared equals y. Or x equals plus or minus the square root of y. Is this the case? Is this true? So essentially, for this function to be 1 to 1, for this function to be 1 to 1, we have to ensure that every real number, for this function to be onto, misspeaking. For this function to be onto, we'd have to ensure that every real number y has a square root. And the answer to this is what? No. If I take -3, does it have a square root? Not in the real numbers, it doesn't. So this only works.
Look at this. KCV deserve this.
If y is an element of 0, infinity. That's it. That's the only way it works. So here's the conclusion. And if you have any questions, you need to ask. If we want this quote unquote largest interval for f to be a bijection, we have f restricted to the non-negative real numbers And the codomain must be the non-negative real numbers. There is no interval that you can define this function on that is larger than 0, infinity in which you have a bijection. So this is a challenging problem. These are conceptually difficult topics for most students at this level, and unfortunately, we're asking you to learn them, and that scares us. So don't be scared. It's so mean of me to say, don't be scared. I remember being clueless when I learned this stuff. Does anybody have a question about this? Now, I called this scratch. I called this scratch work. It's your job so it's now your job to write these ideas up in a clear manner. I mean, that's one of the things you're supposed to practice in this class, writing things up so that people can read them and understand them. That was like one of my favorite things about grading your midterms. Like on that one problem with the sequence, everybody just tells me what the formula is. No one gives me any idea where the hell they got it from. Well, a few of you said you got it from a website, but you should at least have written down how the website showed you how to get it or something. All right, any questions about number 2? How about I just mute all of you guys?
Why do you even do that to yourself?
That's what I should do. I should do that. I have to mute. I meant to do that. I apologize. This is funny. Now I'm not privately. Look, it's everybody gets to see this. Josh, Mackenzie's calling you out. I think you guys should fight. How do I do this to everybody? You guys are funny. I'm not lying to you. I swear to God, and this is going to sound gross. How do I do this? Why can't I just say everyone? This deserves a good laughing my ass off. But I'm not kidding. This summer, or was it the spring? I swear to God, someone was going to the bathroom during class. It sounded like it. I was like, is this really happening? I forget who it was. If I ever figure it out. It's funny, though. How about Amy? This is a good story once. I was in, I like to, you know how I like to tell these things. Did it really? The Supreme Court. Oh, my God. Hey, did anybody watch that crap yesterday? I'm not kidding. Amy was in a meeting. This was back in the beginning of the Rona. And I don't know if you guys remember, but I was like teaching in my, we call it like our game room downstairs / like our downstairs is split up in half. Like one half has like couches and TVs where the adults hang out. And then behind it is like the kids' playroom. So I would always sit like right between there. But all my books and all my stuff that I used to have in my office, which got confiscated when I had children. Anyhow, you don't give a damn. But I go down and get a book and I just walk right behind Amy and I don't have a damn shirt on. So she's in a meeting at work with like 40, 50, 100 people. I don't know. And a lot of them know me. Someone flushed the toilet. See, that's funny. Oh, God, what a time to be alive. I love you guys. Platonically, of course. This is a fun class. By the way, it's advising time. Reach out to your advisors. And if I'm your advisor, email me every 30 seconds until I respond. And tell everybody to take my classes. Even if you don't have to, they'll be fun as hell. All right, anyhow, let's move on. This is a good class so far. I do enjoy this class. I don't like to have favorites because you're not supposed to do that, but let's not be honest. We all have favorites, right? All right, what's the next one we had? Does anybody want to talk about problem 4? Okay, 4? That's a good problem too. So here's what we're going to do. Let's do this one like a fancy schmancy proof. Or do I have to do? I'm not going to do 3. We already did 3, didn't we? Pretty sure we did 3 in class. Yeah, I think we did. Oh my God, 1 to 6. Get out of here. What do the kids say? GTFHO or something like that? Am I supposed to say that? Get them freaking horns off the cow. What a time to be alive. This is what I always text my friends for what a time to be alive. You guys should start doing this. I always do this. Here, I'll just write it here so everybody sees. I do this. WATTBA. What a time to be alive. Watba. In fact, this is good. All right, so we're going to skip 3 because I swear we did it. It's not a bijection. It's not even 1-to-1. 3 is very similar to the exam question, and it's also similar to an example we did, I think, last week or the week before. Now, 4, we assume F is a bijection. So we want to prove whether G is a bijection or not. So here's what we're going to do. We assume F from R to R is a bijection. And then we define G, which also will map R to R. We're going to define this by you take the number 4, you multiply it by F, and then you add 3. And the question is G a bijection? Now, I could have said show that it's 1-to-1 or show it's not, and then show that it's onto or show it's not. But again, at some point we have to understand the bigger picture. The bijection thing is the big picture here. I'm dancing. All right, so what we have to do is we have to show that it's not either 1-to-1 or onto. So here's our sketch. So here's the 1-to-1 part. Now, I got 2 ways to do this. I can take 2 numbers in my domain that are not equal and show that G of that number, or both inputs don't have to be equal. Or I can work the other way. So let's assume there exist how about, let's pick, what letters shall we use? Let's use A and B. Let's assume there exist A and B in R with G of A equal to G of B. Now, can we prove, if we can prove A equals B, that means it's 1-to-1. If we can prove A equals B, then G is 1-to-1. Well, let's do some reasoning here. G of A equal to G of B equals, excuse me, G of A being equal to G of B is equivalent to 4 of F of A plus 3. Is that what it was? F of A? Yeah, plus 3. Being equal to 4 times F of B plus 3. And now, of course, I can subtract 3 from both sides. This is equivalent to 4 times F of A being equal to 4 times F of B. And then I can divide both sides by 4. And this is equivalent to F of A equals F of B. So we have reduced our problem down to F of A must be equal to F of B. And this is good news because we know we have information about F of A and F of B. We have a very important piece of information, and that is F is 1-to-1. Why? Because F is a bijection. So that tells us then that A must be equal to B. That's what this tells us. So how do we sort of, or what do we make of this? Well, we make the following. Since F is 1-to-1, F of B being equal to F of A guarantees A equals B. Thus, G of A equals G of B is the same thing as F of A being equal to F of B, which is the same thing as A being equal to B. And what we can conclude is we conclude G is 1-to-1. Does anybody have a question about this? So all we've done is we've shown that F being 1-to-1 means G is 1-to-1. Now, what about onto? Well, and by the way, here's something that should be pointed out. This is a little dirty secret. I am inclined to think that G is going to be a bijection because I have experience. And I know that if F is a bijection and all I'm doing is multiplying it by 4, think about what this would do to the graph, for example. Multiplying it by 4 only just makes it a little steeper. And adding 3 to it, all it does is shift it up. So if this function F is going to have these nice properties, I would assume just multiplying it by 4 and adding 3 wouldn't change those nice properties. So my intuition tells me F is going to be enough to guarantee G is a bijection. So when I try to do my scratch work here, in my head, I believe that G is going to be a bijection. So I'm not looking for anything bad to happen. I'm trying to show that it works. Whereas in the previous examples we've done, my experience tells me that it's not a bijection. So then I'm looking for something bad to happen. This is what we call experience, you know. Just like the more you drive, the more experience you have. The longer you live, the more experience you have. The more math you do, the more experience you have doing math. It's a funny freaking world we live in. The more code you write, the more experience you have coding a computer. The more you teach, the more experience you have teaching. It's a funny freaking thing. But it is what it is. So I am inclined to believe that it's not going to be hard to show G is a bijection. And in fact, it wasn't. I literally just followed the definition. That's all I did here. I looked at the definition. And I said, okay, the definition says, assume this, assume that the outputs are the same, then that tells us the inputs are the same. And so I said, let's assume that they're there. And I was able to conclude that their inputs were the same. And that means it's 1-to-1. All right, now what about onto? So for onto, what I'm going to do is pick any y in the real numbers. Is there a partner? Is there x in the real numbers with g of x equaling y? How do we show this? Okay, so what usually happens in a mathematical proof is that we have to take advantage of any assumptions we have. Or else why would we write them down? Why state an assumption if it's not necessary? So the big assumption I have is that F is a bijection. We used its one-to-oneness in the previous part. We would think then that we're going to use its onto-ness, or the fact that it's a surjection here. So let's think about how to reason that. Well, since F is 1-to-1, there exists, I'm going to give it a different name, I'll call it Z. There exists Z such that F of Z equals Y. Okay, well, let's just say we don't know what to do. Let's just plug this Z into G and see what happens. We know we're allowed to plug Z in. Z is a real number. What is the domain of G? It's R, so I can plug it in. So what's G of Z? G of Z is 4 times F of Z plus 3. But that is nothing more than 4y plus 3. Now, I don't know if this is going to help me, but I'm going to try it. The reason I'm going to try it is because I know what F of Z is. So I'm going to plug it in. Now remember, I need to find a number that I plug in to G that spits out Y. This is not giving me that, right? But it does give me insight on what might work. Because what am I going to need to happen? I want to find something that when I plug it into G, here's what I need to happen. I need 4 times F of something plus 3 to equal y. So, I need an input. Let's call it, I'm going to give it another, I'll call it W. With G of W equals 4 times F of W plus 3. I need this to equal Y. So this only happens if F of W is equal to Y minus 3 over 4. So now this is at a point where from the perspective of you, the student, or you, the spectator, it might seem like I'm sort of all over the place. And I am trying to sketch what's happening here. This is not a solution that's polished. This is me brainstorming. And I'm trying to brainstorm from the perspective of you, the student, not the trained professional. Let me repeat what I need to do. I need to pick any number out there that's a real number. For G to be onto, I have to find a corresponding guy that I plug in that spits out my number. So my initial thing was, okay, initially I say, pick Y. Is there any guy out there that I can plug in that's going to spit out Y? And so my first instinct was to figure out, or to take advantage of the corresponding Z for F. F gives me one of these guys. I'm calling him Z. But the moment I plugged Z into G, it didn't give me what I wanted. It didn't spit out Y. But it did give me insight to how I can do it. The insight is, oh, okay, I get it. I need this thing right here to be equal to Y. That's what I need. And so instead of me using Z, I am going to say, okay, if W is going to work, here's what needs to happen. And the good news is this W exists. And the same reason it existed, the reason it's going to exist is because F is 1 to 1. So let me write this in red because this is important. This W exists because, F is onto. So let me explain that in more detail on the next page. Indeed, let W be a real number. Then Y minus 3 divided by 4 is also a real number. Would you disagree with that? I don't think so. The difference of two real numbers is a real number, and the quotient of two real numbers is a real number. Since F is onto, there is a real number, which I'm going to call W, such that F of W equals Y minus 3 over 4. Hence, G of W equals 4 times F of W plus 3. And that equals 4 times Y minus 3 over 4 plus 3, which simplifies to Y. Thus, G is onto. That is a challenging problem. Your task is to now take all these pieces to the puzzle that I've written down for you. I mean, I've given it logical background, but how do you piece this together? How do you write it so it reads nicely? What we've done now is just a bunch of gibberish everywhere. And in the gibberish is some true good logic, but you have to piece it all together. How do you write a proof? I mean, that's something I can do that for you right now, but that doesn't help you get good at it. This is a challenging problem. By the way, another way that you could have attacked this that might have led you to the same sort of conclusion is do what you did when you were in an algebra class. Bijection is important. And as I said, one of the reasons we like bijections is because they have inverses. And so one of the things you did in algebra classes is given expressions, you found inverses. And there was a strategy you were taught how to do. They say replace g of x with y, right? And then they would say solve for whatever. They would tell you to do that. And you could have done the same thing here to get this idea, but I'm not pretending that this is an easy problem. These ideas of bijections and this the concept of an abstract function, this is difficult, particularly the first first few times you come across all this. Does anybody have a question about this before we move on? Okay. All right, so the next problem is the number n factorial, which many of you should be familiar with, but if you're not, here we go. There are two ways to define the factorial. So this reads n factorial. So in many ways, it's a shorthand, but it's a very, very important shorthand. So how do you define it? Well, here's definition one. Let n be greater than or equal to 1 be an integer. N factorial equals n times the previous guy times the previous guy all the way down to 3, 2, 1. And then we also define 0 factorial to be 1. So let's just look at some examples. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. And this goes on forever. So these products show up in lots of different places. If you've taken calculus, you've seen these products. If you've ever taken prob and stats, you've seen these. They come up in counting arguments. So the shorthand we adopt for these products that are in like this decreasing order is factorial. So this is one definition. But alternatively, you can define it. And by the way, does anybody have a question about this? Okay, so an alternative definition that is often useful is this recursive definition. They're equivalent, and that is set 0 factorial equal to 1 and 1 factorial equal to 1. And then for n greater than or equal to 2, n factorial is defined as n times n minus 1 factorial. So this gives you the same thing, but you just think of it differently. So examples, what's 2 factorial? Well, that is 2 times 1 factorial, which is just 2 times 1, which is 2. And then 3 factorial is 3 times 2 factorial, which is, of course, 6. And then 4 factorial is 4 times 3 factorial, which is 24. You get the idea. And we sort of mentioned this before. I think we actually went through this last week, didn't we? We talked about this idea between recursive and explicit. And I even mentioned, imagine asking a computer to compute these things. What would be quicker for a computer to compute it using this definition or the previous one? All right, so once we have that sort of definition, we can do problem 6. I wanted the first 10 terms of this sequence, which is going to require a calculator. If a sub n is n factorial minus 2 to the power n, what's a sub 0? A sub 0 is 1 minus 1, which is 0. A sub 1 is 1 minus 2, which is negative 1. A sub 2 is 2 minus 4, which is negative 2. A sub 3 would be 6 minus 8, which is negative 2. A sub 4 would be 24 minus 2 to the 4th is what? 16. And so now you're positive. A to the 5th is 120 minus 32. So that would be 20 and 67. So what is that, 87? If I do that correctly. No, 80, not 87, 88. And then I think you guys can finish that out. Probably going to need a computer or a calculator, but does anybody have a question about this problem? Uh-oh, did I make an error? The chats are coming in. Yeah, we're going to get there. We'll get there, Dimitri. We're getting there. All right, now, I like this sequence. This sequence is pretty cool because it starts going negative and then it comes positive. It's a pretty interesting sequence. Okay. So the next thing was very similar to the problem we gave you on the exam. So let's briefly look at how you could think about 7. I know we did this already, but actually no, we did it on Monday. So almost the identical problem was done on Monday. So check those notes. So now we get to 8. 8 is a tricky one. So we're given that a sub 0 is equal to 1, and that's also equal to a sub 1. And what we're trying to do is, can we figure out, I mean, we'll be able to figure out the sequence, but can we find a formula? So what's a sub 2? Well, here's what we know. So I'm going to take what I'm given, and I'm going to say, here's the formula we start with. We call this, as I said, a recursive definition. We know that the nth plus 1 term is n minus a sub n minus a sub n minus 1. So I just rearranged. So this tells us that a sub 2 would be equal to 1 minus a sub 1 minus a sub 0. So this is going to be a tricky thing for us, these subscripts. So if my left-hand side, if n is 2, I get a sub 2, excuse me, if n is 1, I get a sub 2 equals 1 minus a sub 1 equals a sub 0. And if you want, if I can squeeze it in here, what is a sub 3? That would be 2 minus a sub 2 minus a sub 1. So what we're looking for is there's some sort of formula we can gain from this. And it's not easy to do this. In fact, you have to be pretty creative. Okay, so is there any sort of strategy that we can do similar to problem 7 where we keep breaking it down more and more and more? And it's not as direct as perhaps the previous stuff was. Or excuse me, like problem 7 is. So here's an idea. Let's start with, say, a sub 4. So what do we know this means? We know this means 3 minus a sub 3 minus a sub 2. Now, is there anything can I replace a sub 3 and a sub 2 with anything that is useful? Now, what does useful mean? Well, again, like in problem 7, I'm looking for some sort of pattern. You know, perhaps I try to break it all the way down to the very, very bottom. Like, what if I replace, if I replace a sub 3 with what a sub 3 is? So, we had on a previous page what a sub 3 is equal to. A sub 3 is this. So what if I plug that in? What happens? And again, I'm not suggesting this is going to work right away. But I know a sub 3 is 2 minus a sub 2 minus a sub 1. Well, that gives us that a sub 4 is equal to 3 minus 2 minus a sub 2 minus a sub 1, and then it's minus a sub 2. And does that clean up? Well, we get 3 minus 2, which is 1. The a sub 2's will cancel, so I'm left with plus a sub 1. Now, why is this useful? Well, we know what a sub 1 is. By definition, it's just the number 1. So this is a sub 2. Or excuse me, this is just 2. This is 1 plus 1, which is 2. By the way, this should not be a parenthesis here. I don't know why I wrote this. This should not. Now, this doesn't really help us. We could have calculated this from the pattern before, but it might give us an insight on where if there's some other pattern we're not seeing. Okay, so the question then becomes, what do I do now? Am I at a dead end? Is there something else I can do? Well, let's look at what happens again. What about a sub 5? So a sub 5 we know is 4 minus a sub 4 minus a sub 3. And if we play the same strategy we did before, we can replace a sub 4 with something. Well, what's a sub 4? That is 3. And then it would be minus a sub 3 minus a sub 2. And then, of course, we're left with minus a sub 3. And once again, the a sub 3's will cancel. So now I'm left with 1 plus a sub 2. And this is equal to 1 plus 2, and this is 3. So on one hand, we got a sub 2. Well, what is a sub 2? A sub 2 is a negative number. A sub 3, okay, let's go back. So
wouldn't a sub 2 be negative 1?
I just said a negative number, right?
Yeah, so it'd be, never mind.
What, say that again?
So we just did 1 plus a sub 2, which may be 1 minus 1.
What do you mean 1 plus a? I'm not quite sure what you're talking about.
Go to the last slide.
This one?
No, like the very last one.
Yeah.
The one we just did.
Yeah, so what should this be?
Yeah, shouldn't that be negative 1?
Yeah.
I hate
Right.
when you do that.
Why do you hate when I do that? I gotta make sure you guys aren't sleeping.
Because now I'm really confused.
You shouldn't be. Don't say that. I mean, you shouldn't say you're really confused. And the reason for that is we have to make sure that we're following along. And if I have to go back to the previous page to stir some imagination, well, then that's what I have to do. Now let's ask ourselves, is this even correct? I mean, look, if we go back to I told you this is tricky. If we go back to the first page, let's come over here. Let's just look precisely at what's happening. So we know that a sub 0 is 1. A sub 1 is 1. You with me there? So what's a sub 2? Well, a sub 2 has to be satisfying a certain thing. So we can think of it satisfying this. And so a sub 2 would be the case when n is 1. So you would get 1 minus a sub 1 minus a sub 0. And so if you do the math here, you get -1, correct? Now what happens for a sub 3? Well, a sub 3 becomes 2 minus a -1. Excuse me, minus a -1, which would be 2 plus 1, which is 3. 3 minus 1 is this becomes 2. Then what's a sub 4? Well, on the next page, we thought we did a sub 4 correctly, and it worked out. It doesn't look like we messed it up. It looks like we get 2. And then a sub 5, provided we didn't make any mistakes. For a sub 5, we get 0. We think. So again, it's not at all clear if this pattern, if there is a pattern, and what we're supposed to do about said pattern, if we think there is one. Does anybody have a question or a comment about this? And actually, I'm going to stop with this because this is going to be an extra credit problem if anybody wants to tackle it. So we'll leave you to that. And I'm not suggesting it's obvious. This is a very tricky problem. But if any of you are inclined to use a computer, you might want to have the computer calculate a bunch of these, and you might see the pattern a little, I won't say easier, but a little better. All right, so anyhow, this is, I'm not going to grade this particular problem if you get it wrong. If you get it right, I'll be very excited. But this is left as extra credit. Because what I do want to do real quick is I want to finish the last 2 problems in case anybody has a question about them. I don't suspect people do, but we have to cover all our Okay, so number 9. Here's what you should know. So we should know that the sum k goes from 1 to n of k, which is 1 plus 2 plus 3. You guys should know that this is n times n plus 1 over 2. So I don't want to steal the fun from you, but this problem that I'm asking you to do, so the sum, k equals 1 to say 78 of k, which is 1 plus 2 plus 3, and this goes all the way out to 24, and then plus 25, and goes all the way out to 78. Well, this piece right here is 24 times 25 over 2. And this piece right here is the sum we're asking you to do. This is just one way to think about it. And of course, what is this number over here? So hopefully you can use this to reason that this is what the answer is. And maybe you can write it a little cleaner than this. So it's just a subtraction. Anyhow, hopefully you guys can put these pieces to the puzzle together. I don't want to steal your thunder. Any questions about 9? I just realized you guys had questions about 8. Or for 7, Dangle, yeah, that works. We did that problem on Monday. You should check it out. And then that is not correct, Ethan, for that. I don't believe. No, it's definitely not going to be that. All right, our last one. Yeah, number 8 is not easy. It's a very challenging one, but I put it there on purpose. We'll see if anybody wants to try it. Okay, the last thing we'll talk about is 10. 10 is very similar to 9. You just need to know the formula. So this is something I think we went through it, did we not? I thought we did this problem. So I don't want to steal the thunder, but you need to use this guy. Or how did I write the problem? Did I start at 1? I don't remember how I just lost the homework. Yeah, I started at 1. Oh my God, I can't believe I just lost it. Does anybody remember? First off, I can't have it. No, this is a number n. What is this equal to? Does anybody remember? Same thing. Same thing.
Are you asking what you have on the homework?
Well, no. I'm asking if anybody remembers what this is equal to. Well, so first off, note that this is 1. I think we did this, did we not? I thought we actually showed you the formula. First off, this is equal to this. I think we did it last week, but we got to go. We're over time. It's in the book. It's not hard. It's a very simple formula. Maybe not last week, 2 weeks ago. It's not hard. And it's not hard to derive either. I know I'm almost positive we derived it. In fact, I know we did. Yeah, we absolutely did. So anyhow, check it out. I think it was 2 weeks ago. Look in your notes. If you guys don't have any questions, we're over time, so we got to go. All right. Thank you very much. If you have questions, please let me know. And you guys have a great weekend. And if you email me if you have any issues. Thank you guys. Take care.